every method which has a great advantage in studying something will also have some limitations somewhere. We have spent quite a few lectures on isothermal titration calorimetry and discussed a lot about its advantage, that this technique is able to give us the thermodynamic signatures in just one single experiment. However, the limitations of isothermal titration calorimetry are, number one, the solubility. The solubility of several drugs in aqueous solutions is very poor, and therefore the choice of other solvents which can assist the solubilization of the drugs has to be done with care. We cannot use alcohol because the heats of dilution of alcohol are enormously high. Therefore, alcohols should be avoided in isothermal titration calorimetry. Similarly, if we use a certain percentage of DMSO or carbon tetrachloride or other things, we have to worry about the excessive heat of dilution. We have to worry about the effect of these kind of solvents on the conformation of proteins. The second limitation with isothermal titration calorimetry is that we cannot very accurately determine the values of binding constants which are very, very low and very, very high. So therefore, even though there are large advantages, many advantages of isothermal titration calorimetry, these are also associated with some disadvantages or some limitations, not disadvantages. These are also associated with some limitations. Suppose if the binding constant is of the order of 10 raised to the power 20, 10 raised to the power 30, 10 raised to the power 40 or even higher, then can we use isothermal titration calorimetry? The answer is we can use isothermal titration calorimetry, but the best thermodynamic parameter which is obtainable from such an experiment will be the enthalpy of binding. It will be difficult to get the value of the binding constant with great accuracy. And as we will discuss in this lecture, that differential scanning calorimetry can be used to estimate the binding constants in strong to ultra tight protein ligand interactions. But before that discussion, let us take a look at what is the range of binding constants that can be determined by different methods. Let's take a look at the slide. The recommended range of binding constants in isothermal titration calorimetry is 10 raised to the power 2 to 10 raised to the power 9. The binding constants which are less than 10 raised to the power 2 and higher than 10 raised to the power 9 cannot be very accurately determined by isothermal titration calorimetry. For reactions of 1:1 stoichiometry, most chemical and optical methods fall in the binding constant range of 10 raised to the power 5 to 10 raised to the power 7. And whereas if you use the fluorescence, you can extend this range to 10 raised to the power 10. We have already discussed how to use fluorescence in estimating the value of binding constant. Single site binding constants of the order of 10 raised to the power 40 or larger can be estimated by DSC. Which goes well beyond the range that is accessible to other methods. So in this lecture, we will be discussing the use of differential scanning calorimetry in estimating the values of binding constant. And in one of the previous lectures, when I was discussing how to get the enthalpy of ligand binding by DSC, we showed these kind of transitions, that is, if protein is only in the native form, it will show this kind of thermal unfolding, and if it is bound with the ligand fully saturated, PL will appear at a higher temperature. Now let me define some thermodynamic parameters associated with these transitions. Let us call T0 as the transition midpoint in the absence of ligand, that is for the blue line. Tm, the transition temperature in the presence of ligand, that means it is for the green line. Lt and Pt, the bulk concentrations of ligand and protein. These are the total concentrations of ligand and protein taken in the study. Delta Ht and Kt we will refer to parameters for the reaction at the general temperature T. And prime we will use for the unfolded state. P prime means we will be talking about the unfolded protein. And wherever I use the subscript EQ, equilibrium, for example KEQ, this will be equilibrium constant for the unfolding process monitored by DSC at transition midpoint. So let us keep this in mind. Whenever I use EQ, this will be corresponding to the process which is monitored by DSC at transition temperature. Now, when we do any reaction, when we study any reaction, and later on want to express this reaction in a quantitative manner, as we have discussed while discussing the equilibrium constant, that equilibrium constant should be expressed in the terms of activities. And then we make certain assumptions. For further discussion, we will also make some assumptions, and let us take a look at those assumptions. The common assumptions which we will make here are, one is that all the transitions we will be assuming that these are two state. We will not assume that there is an intermediate state, because that will make our treatment very, very complex. Let us start with the simple treatment. The second assumption that we will make is that a ligand binds only to the folded form. In other words, if I have P and if I have P denatured in the mixture and I add a ligand, ligand has only affinity with the native form and it does not bind with the denatured form. That is assumption. The third assumption is that all delta Cp values are temperature independent. And the fourth assumption is all activity coefficients are unity. We are making a lot of assumptions here. And as you will see when we discuss the mathematical treatment, that if we remove all the assumptions, then how the treatment becomes more and more complex. It can be done, but let us first begin with a simple process in which these assumptions are valid. Okay, this is Van 't Hoff equation. We have discussed many times. Van 't Hoff equation can also be manipulated and rewritten. Mathematical manipulation of this allows you to write in this form. And one can go this further with this step and express KT2 is equal to KT1 into exponential minus delta H naught by R d1 by t from T1 to T2. And then it is possible to arrive at these kind of two equations where we express the temperature dependence of the values of K. I will just explain one of these and the other you can try yourself. Let us start with the Van 't Hoff equation, which is d log K by dt, of course at constant pressure, is delta H naught by RT square. So actually it is a partial derivative at constant pressure, but for the sake of integration I am just writing d log K by dt as delta H naught by RT square. Now delta H naught at any temperature I can write as delta H naught at T1, let's say if T1 is my reference temperature, plus delta Cp, of course it will be naught into T minus T1. This is by using Kirchhoff's law, because this is at any general temperature. Now I can substitute this over here. So what I have is now d log K by dt is equal to delta H naught at T1 plus delta Cp naught into T minus T1 over RT square. Let me go a step further. D log K by dt is equal to delta H naught at T1 over RT square plus delta Cp naught over RT minus T1 delta Cp naught over RT square. And I can integrate this. K from KT1 to KT2, from T1 to T2, T1 to T2, T1 to T2. And what do I get? I get log K T2 over K T1 is equal to integration of this is going to be delta H naught at T1, which is constant, by R and you have T minus 1 over minus 1 minus 1 from T1 to T2 plus delta Cp naught over R log T2 by T1 minus T1 delta Cp naught by R. Again I have minus 1 by T from T1 to T2. And you have to now apply the limits and solve for the final equation. So once you solve for this, what you are going to get is log k T2 by k T1 is equal to minus delta H naught by R into 1 over T2 minus 1 over T1 plus delta Cp naught by R log T2 by T1 and plus T1 delta Cp naught by R into 1 over T2 minus 1 over T1. So what I have now is log k T2 over k T1 is equal to minus delta H naught by R 1 over T2 minus 1 over T1 plus delta Cp naught by R, and I have log T2 by T1 plus T1 by T2 minus 1. Now let us take a look at this slide. So we are now at this expression. We have derived this expression. I have removed log and brought an exponential factor. So if you take the reference temperature as T1, you come up with this equation, and if you take the reference temperature with T2, you can come up with this expression. Let us keep these two equations in mind, which will be used thoroughly in the next discussion. We will discuss binding stoichiometry of 1. And if you understand the treatment associated with the binding stoichiometry of 1, then you can also deal with the further complexity, that is when the binding stoichiometry is 2 or 0.5 or any other. And also we will restrict to single unfolding transition to keep the discussion at relatively to begin with an easy discussion. Let us take a look at this table. We are talking about protein unfolding to P prime. Prime, as I said, we will use prime for the unfolded state. So when P goes to P prime, the associated equilibrium constant obviously is concentration of P prime divided by the concentration of P. And the parameter set which are associated with the thermal unfolding are T0, delta H at T0 and delta Cp. T0, as we initially discussed, correspond to the transition temperature. And when this protein is associated with a ligand, then what we have is P plus L is equal to PL. The equilibrium constant KL, this is what you will be interested in. KL is equal to concentration of PL divided by concentration of P into concentration of L. And we can also, get the parameter set, the values of K at T0, delta H, L associated values at T0 and delta CPL values under standard state conditions. So now let us start one by one with the equations. The first equation that we are talking about is P is in equilibrium with P prime. P prime is denatured state. And associated value of K is equal to concentration of P prime over concentration of P. And if now I have to write K equilibrium at temperature T, for this I can write the concentration of unfolded form divided the concentration of folded form. What is the concentration of unfolded form? Is P prime is unfolded, and the folded, if you have P and PL both in the solution. Now you see, P plus L, when they are forming PL, your KL is defined as concentration of PL over concentration of P into concentration of L. So now what I will do is, I will choose PL from here, P prime from here, and substitute in this. So what I have is K equilibrium at T is equal to P prime. P prime is equal to K into concentration of P divided by, let me retain P, plus PL is equal to KL into concentration of P into concentration of L. So you remove PP from here, I can write this as K. Now let me specify at a temperature T divided by P plus KL at temperature T into L into, if I retain P, into P. And P can be cancelled. So once you cancel this P everywhere, take a look at the slide. We come up with this equation, that K equilibrium at any temperature T is equal to K at any temperature T divided by 1 plus KL at any temperature T into L. That is the ligand concentration. Now if I express in the presence of ligand K equilibrium at Tm, Tm is the temperature where the transition is half complete, and we have discussed several times that the value of equilibrium constant when the transition is half complete is equal to 1. And now what I will do is, instead of T, you just write Tm. The description is same. So it becomes K at Tm over 1 plus Kl at Tm into the concentration of ligand at the midpoint of transition. So I hope that these two derivations are very, very clear, because if we understand, for example, this one, let us write this down and work on this. What we have derived is that K equilibrium at Tm is equal to 1, and we have shown that this is equal to K at Tm divided by 1 plus Kl at Tm into concentration of the ligand at Tm. So from this I can write this equation, this equality, 1 plus Kl at Tm into concentration of L at Tm is equal to K at Tm. And from this I can write Kl, because we are mostly interested in Kl, which is the binding constant associated with the ligand, is equal to K at Tm minus 1 divided by the concentration of L at Tm. This result connects with the Kl and the concentration of ligand at Tm. Now Kl at Tm or K at Tm, these can be connected to enthalpies of reaction and the values of the equilibrium constants at any temperature by the equations that we derived earlier. Let me show you back the equations which are required for discussion. I'll have to go back by these slides. You see, these two equations connect the value of K at any temperature with the value of K at an initial temperature and the corresponding values of enthalpies, heat capacity changes and the temperatures. So by making use of these equations, we will extend our discussion to derive further properties. So what we have at present is this expression. By the use of differential scanning calorimetry, we can easily get the transition temperature, calorimetric enthalpy and the change in heat capacity associated with the unfolding in the absence of ligand. Then we can design another experiment and run a DSC. And in that experiment, you first make a complex of protein with a ligand and then thermally unfold it. What you will get is the transition temperature here, we will get the calorimetric enthalpy and we will get the delta C. We have these 6 input parameters. 2 transition temperatures, which are, what are these? Transition temperature in the absence of ligand, transition temperature in the presence of ligand. We have 2 values of enthalpies of unfolding. One, enthalpy of unfolding in the absence of ligand, and enthalpy of unfolding in the presence of ligand. And we have the corresponding values of delta Cp. These will be the input parameters for the further discussion. Now, the other things which are required are the values of enthalpy of binding and heat capacity of binding. Can the enthalpy of binding be determined by differential scanning calorimetry? Yes, enthalpy of binding can be determined by differential scanning calorimetry. We have discussed in one of the lectures that if you study the thermal unfolding in presence of ligand, in the absence of ligand, and then the difference between the two, the enthalpies, can be the value of delta H of ligand binding weighted by their fractions. We need to know what fraction of the protein is ligated to calculate the value of enthalpy of ligand binding by use of differential scanning calorimetry. We will need to develop few more equations and go into details on how to get the value of binding constant associated with the ligand. That is the main aim. And then also discuss how to get the simulations, how to do the simulations. We will discuss the equations which are required for simulations, come up with an expression for excess enthalpy, derivative of which will give the heat capacity. And then we will discuss how the fitting of this theoretically generated curve with the experimental data points can help us in getting the value of the binding constant. So, we still need to complete the discussion by deriving more equations. What we have discussed in this lecture is very first the basic reaction that we are studying, that is single binding reaction, single unfolding transition, the associated equilibrium constant and parameter set, and then we have derived some equations which connect the values of equilibrium constant from one temperature to another temperature in terms of enthalpies and the associated heat capacities. You will appreciate more about this discussion once we complete the whole discussion associated with this process, and that we will discuss in the next lecture. Thank you very much.